From planets to black holes, space is full of extremes. And today, we are going to focus on one of the smallest but most extreme objects in the universe, the neutron star. Neutron stars are so dense that if you were to take a teaspoon of their material, it would weigh about 4 billion tons. That's heavier than 8,000 African elephants or 32,000 grizzly bears. To put this into perspective, it's like trying to lift the Empire State Building with just your pinky finger. So how can something be both extremely small and extremely heavy? Let's start at the beginning. A teaspoon of anything is pretty small. There are 5 grams in a teaspoon, but the mass of an object isn't just determined by its size. It also depends on what the object is made of. If our teaspoon is filled with lead, it will weigh much more than if it's filled with feathers. This is because lead is much denser than feathers. Density is a measure of how much mass is packed into a given volume. Objects that have a lot of mass packed into a small volume are dense. Objects with less mass packed into the same volume are less dense. To make our teaspoon as heavy as possible, we need to find the densest substance known to science. That title belongs to nuclear pasta, found on the surface of neutron stars. Nuclear pasta is so dense that 1 cubic centimeter of it weighs around 10 billion tons. To put that into perspective, that's as heavy as 1 million people. Or, think of it this way, you could fit 27 trillion of these cubic centimeters into the volume of a single teaspoon. But where does all this extra weight come from? Let's go back to the beginning of the story. The neutron star itself. A neutron star is the incredibly dense remnant of a massive star that has exploded as a supernova. When a star explodes, all the matter inside is thrown out into space. What's left behind collapses in on itself under the force of its own gravity. The remaining core is then squeezed into an incredibly small space. Let us take an average-sized neutron star with a diameter of 20 kilometers and a mass of 1.4 times that of the Sun. That's about 300 trillion Now let us take a teaspoon of this neutron star and see how much it would weigh on Earth. We know that the volume of a sphere is 4/3 times pi times the radius cubed. So the volume of our neutron star is 4/3 times pi times 10 kilometers cubed, which is about 4,200 times 10 to the 12 cubic meters. We also know that density is mass over volume. So we can calculate the density of our neutron star by dividing its mass by its volume. That gives us a density of about 340 kilograms per cubic meter. That's about 100 trillion times denser than water. Now let's see how much our teaspoon of neutron star material weighs on Earth. We know that 5 grams is equal to 0.005 kilograms. So, the mass of our teaspoon is 0.005 kilograms divided by 340 kilograms per cubic meter, which equals 1.5 times 10 to the 8 cubic meters. Now let's convert cubic meters to teaspoons. We know that 1 teaspoon is equal to 5 cubic centimeters or 5 times 10 to the 6 cubic meters. So the volume of our teaspoon of neutron star material is 1.5 times 10 to the 8 cubic meters divided by 5 times 10 to the 6 cubic meters per teaspoon, which equals 30,000 teaspoons. Finally, let S multiply the number of teaspoons by the mass of a single teaspoon to get the total mass. That gives us 30,000 teaspoons times 0.005 kilograms per teaspoon, which equals 0.15 kilograms or 150 grams. That's right. A teaspoon of neutron star material weighs about 4 billion tons on Earth. Now imagine trying to carry that weight. If you were to hold a teaspoon of this material, it would feel like you were holding the entire weight of almost 8,000 African elephants. You'd probably be utterly crushed into a pancake on the spot. And that's not even the weirdest part. As you dug deeper into the neutron star, you'd soon reach the pasta, the incredibly dense matter found on the surface of neutron stars. This matter is so dense that 1 cubic centimeter of it weighs about 10 billion tons. That's heavier than 1 million people or 100,000 school buses. So, if you were to take a teaspoon of nuclear pasta, it would weigh about 40 billion tons. And if you were to hold that in your hand, you'd be utterly crushed into a pancake on the spot. To understand how matter can be so dense, we need to look at what it's actually made of. Everything in the universe is made of atoms. Atoms are the smallest unit of matter that still retains the chemical properties of an element. They are incredibly small, and there are about 10 to the 8 of them in a single teaspoon of material. Atoms themselves are made up of even smaller particles called protons, neutrons, and electrons. Protons and neutrons are found in the nucleus of the atom, and they're held together by the strong nuclear force, one of the 4 fundamental forces of nature. Electrons orbit the nucleus in shells. When you look at the structure of an atom, you can see that there's a lot of empty space between the nucleus and the electrons. If you were to remove the electrons from an atom, it would collapse in on itself, because the protons would no longer be shielded by the negatively charged electrons. In neutron stars, the protons and electrons are squeezed so close together that they combine to form neutrons. This means that neutron stars are made almost entirely of neutrons, which are uncharged particles. Because there's no electrostatic force pushing against the neutrons, they're able to pack in much closer to each other than protons and electrons. The reason why they don't collapse further is because of the Pauli exclusion principle, a quantum mechanical principle that says that 2 fermions can occupy the same state. Fermions are particles with half-integer spin, such as neutrons. In order for neutrons to continue packing into a given space, they must occupy different quantum states. This means that there's a limit to how close they can be packed together. As you approach the center of a neutron star, the pressure and temperature increase dramatically. At some point, the protons and electrons are squeezed together so tightly that they can no longer exist as separate particles. They merge to form neutrons. The star continues to collapse until it reaches the point where the neutrons are packed as tightly as they can be. This is the neutron star's core. Some physicists believe that the core of a neutron star is actually a quark star. Quarks are elementary particles that are thought to make up protons and neutrons. In a quark star, the protons and neutrons are broken down into their constituent quarks, which are then squeezed together. The exact mechanism by which neutron stars form is still unknown, but it's believed that when a massive star explodes as a supernova, the core is left behind. This core is then squeezed in on itself due to the gravitational force. As the core collapses, the protons and electrons are pushed together so tightly that they merge to form neutrons. Eventually, the neutrons are packed as tightly as they can be, and the collapse comes to a halt. If the core of the neutron star is made of quarks, then the star is called a quark star. Neutron stars are incredibly small, typically only a few kilometers in diameter. They're also extremely dense, with a teaspoon of matter weighing billions of tons. Neutron stars have been observed to rotate very quickly, and some of them emit beams of radiation that sweep across the galaxy like a lighthouse. These are known as pulsars. One of the most famous pulsars is the Crab pulsar, which is located in the constellation Taurus. The Crab pulsar is the remnant of a supernova that was observed by Chinese astronomers in 1054 AD. The pulsar rotates 30 times a second, and it is believed that it is powered by the energy released from the collapse of a neutron star. Another interesting feature of neutron stars is that they have extremely strong magnetic fields. These magnetic fields can be trillions of times stronger than the Earth's magnetic field. The magnetic fields are thought to be generated by the rotation of the neutron star, which induces electric currents in the star's crust. Neutron stars are also incredibly hot. The surface temperature of a neutron star can reach millions of degrees Celsius. This heat is generated by the gravitational energy released as the neutron star collapses. Overall, neutron stars are some of the most extreme objects in the universe. They're tiny, dense, hot, rapidly rotating, and powerfully magnetized. If you enjoyed this video, please subscribe and check out our other videos on the most extreme objects in the universe, such as black holes and quasars. And if you want to learn more about space, check out our website,